So good afternoon, everyone. Yeah, thanks for a kind introduction. There's an update here. I will present this multidisciplinary work between SINTEF Digital, SINTEF Industry, and Institute of Analytical Chemistry in the North, in Czech Republic. So I've divided my talk into two sections. So perhaps not all of you know SINTEF. I will first say a few words about our institute. Then I will give the background for the electrospray because it's not really like intuitive technique. And afterwards, move to divide concept process flow and show some of the examples of the measurements that we've done. So SINTEF is one of the Europe's largest research organizations, and our vision is technology for a better society. In the core of SINTEF Digital is our clean room. It's called Mina Lab. So we are located in the south of Oslo, and we do different types of MEMS, varying from radiation sensors, piezo MEMS, and environmental and medical sensors, the group I come from. So we do batch processing on 6-inch wafers and different types of projects, clean room-based projects like prototyping and process development, integration, and also feasibility studies. But before I move to introduction of the device, I wanted to say a few words about the background for this field of research. So we do this electrospray interfaces for the mass spec, and mass spectrometry is a great technology because it combines separation and detection based on mass to charge ratio. It's highly sensitive, it's fast, requires small sample volumes, and it's also versatile, so you can do different types of analysis with it. And important thing is that mass spectrometry is almost always coupled with some separation techniques like liquid chromatography or capillary electrophoresis or other technologies. And prerequisite for mass spec is actually to be able to transfer your liquid sample into gas phase, because majority, more like 90% of all of the separations, they are run in the liquid phase. And this is where electrospray ionization comes into play. So electrospray has been introduced by John Fan, we actually got the Nobel Prize in 2002 for chemistry, shared it with two other researchers. And essentially, this method is based as shown on the left side. So you can have like a hollow needle, and if you spray, if you introduce your sample inside this needle and apply high voltage, so at some stage when you increase your voltage, you will form a gas. And then after forming a jet, you will form droplets, which will become smaller, 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 and you will finally ionize your sample. This is one of the few techniques for ionization of the samples for introducing that to mass spec, but it has several advantages. It's a soft ionization. So for example, such components like proteins, then they are not destroyed when you use it. It's also polarity dependent, so you can work with positive or negative ionization modes, although most of the time it's positive, which is used. It can produce multiple charged ions, and it's important also to analyze different types of settings, different types of applications. And it can be coupled with HPLC, C, or GC even. So here I show on the right side, again, kind of principle where you don't have the potential, you form a small droplet at the end of your capillary or the interface, then you start applying the potential, the droplet starts elongating, and at some stage you form this clump. And on this side you see also the graph, which is basically the main idea behind is to say that this process is very dependent on the potential that you apply, and at certain moment you start forming a droplet jet, but it's really unstable process. But if you are increasing the voltage, you enter a stable spray performance. If you are a little bit below, you are unstable. If you are above, you start splitting your plum, or you access kind of the range of the coronal discharge. So it's very narrow range of operation where we want to be. But if you do everything right, then you start spraying your sample into the mass spec sampling unit. But it's really a small portion actually of your sample which enters the mass spec. And to really profit from this technology, and this is where the electrospray miniaturized electrospray interfaces are important. Because if you go down with your flow, then you increase the sensitivity. So you want to have smaller volume and smaller flow rate to really profit from this technology. And also coupling with the capillaries can be easier when you make the miniaturized interfaces for ionization of your sample. Also, one of the backgrounds in this presentation, we work with so-called liquid junction, which is shown on the bottom, and it combines all of the advantages with other two modes of the electrospray interfaces which are available commercially. Maybe in 90% of the cases, it's chiplet interface, which is on the top. But as you see, it struggles in terms of sensitivity and optimization. So our work in this case has more like a unique feature that we try to not compromise on that. So now back to the device. By the way, SINTEF's work is related to the design and fabrication, so everything related to the application and coupling to the MS is our partners in Czech Republic. So it's a little bit hard to introduce that topic, but our device is made in silicon, and we structure it from both sides. From the top, where we form the fluid pillar, which will be the spray, and on the back side you have a star-shaped structure shown here for coupling of the liquid junction. Here is also one of the images of the actual devices. It's 10 by 10 millimeter, and you see here also zooming on one of the pillars. In this case, we had a device which we bonded with glass, just to help our partners to make it more stable, because the handling is an issue where you try to make all this complicated assemblies to couple it to the glass. Our design, so one of the first layouts, we have 124 chips, and we had different design variables, but main to mention are the inner diameter of the spray and the number of the sprays per chip. Most of our work is actually done on the 7 micron chip device and single spray per chip. It's a 5-mask process. 6 masks you can use for glass if you want to bond it for stability with one more glass wafer. And here I show very briefly the process flow. So we start with the silicon wafer. On the blue, we do the backside etching just to have the alignment marks, which will be used for follow-up lithography steps. Then the top side, we deposit 60 CVD layer, which is about 2 micron thick. We structure it, and now the CVD together with the copper disc will be the next layer for Bosch process to etch about 100 micron deep spraying channel. We continue to use the same 6 oxide and structure the spool around the tip. At this stage, we start to finish structuring the top side, and we deposit a very thin thermal oxide, which will be used as an etch stop for follow-up etching processes on the back side. We need the oxide on this side as well, which will serve as an attachment in the RNA process. And we have like a nice treat where it's a double-step etch process where you first etch half depth, the widest area of your star structure on the back side, and then you continue etching and you end up with a section like this. As the last step, we need either to deposit oxide or nitride, or a combination of oxide and nitride to be able to isolate the sample, which we will be spraying from this substrate. Here you see high resolution SAM images of our devices. So we were able to make actually single devices, 5 sprays and also 12 sprays. And in that end, you see also the star-shaped feature for coupling of the capillaries, and these are the same for all types of our devices. Maybe to mention, so in this work, we were able to fabricate these variants where you have an array and where you have the single device on the same wafer, and it was reproducible in terms of the depth of the spraying channels and also size of the scallops during the wash process. Next, the chip had to be assembled, and for that we also tried different types of support. I will not spend a lot of time on it, but basically those supports were used for convenient coupling of the capillaries to the chip itself when you put it to the mass spec, and for the alignment as well. So here you see two of the versions of our interfaces that we've used. Our partners in Norway and Czech Republic, they've also built this setup. The main parts of this setup are the power supplies, which are used to apply potential to the liquid which you are spraying, to the chip itself, and for the stabilization of the assay. And it has laser and cameras to monitor the spraying process during the testing. In the initial test, instead of the mass spec, we've used basically an electrode which simulated the mass spec, and later on when we found the conditions for optimal performance of these devices, we've used the experiment with the mass spectrometer. Here I'm summarizing the test parameters which were mainly used. So we, out of all of the chip variants that we have, most of the tests are done with 7-micron inner diameter tape. And there were 4 spraying buffers that our partners used, and we see also quite a wide range of voltages that they've tested, and quite a wide range of the back pressure for the folks. Hopefully it works now. So you see an example of the spraying. So here it's disappearing because we are moving the laser, and you can see that this part is an electrode which is the mass spec kind of instead of the mass spec. And the plump, I'll try to start it again, is disappearing, and that's exactly what you want. You first want the plump to be formed, and then you want this ions to kind of disappear. That means that it's actually working exactly as intended. And that's the final image that I wanted to show. The same setup was also placed in front of the mass spectrometer instead of the model electrode. And our partners were testing it with a calibration solution, which is often used in mass spectrometry just to demonstrate that it's indeed working. And now we are also developing an actual application on that. So acknowledgements are to Norway Advanced and our partners in Czech Republic in Norway, and some people in SINTEF who were also involved in it. Yeah, thanks to you if you have any questions.